Hi, and this is going to be the spreadsheet addition to the lecture from Chapter 5, Risk and Return. And in this spreadsheet, I'm going to go over the formulas and the demonstrations of how to calculate many of the mathematical aspects of the chapter, which I find very difficult to do over a PowerPoint presentation. So if we want to calculate the holding period return, here's the basic formula. So when you set the formula up in Excel, use equals to start the formula. I'm going to use parentheses for the beginning part where I take ending price minus beginning price plus dividend, close parentheses, and I'm going to divide that by the beginning price. So this gives me a return. I'm going to form that as a percent. So this is going to be a 30% return. And we'll call this the boom, which is the best result possible. If we do for the bust, you can pause the video, take a second to try it yourself. I'm going to redo the formula again. Ending minus beginning plus dividend divided by beginning price. And to copy this, I can just go to this paintbrush and quickly copy this format. And you can see I've also written out the formulas below here, so you can see how they're, if you longhand, how they're being calculated. Okay, so that's the holding period return, pretty simple. Now let's move to the dollar-weighted return. This was exceedingly problematic in the slides because the example in the slide had was incorrect. They had a couple of errors in that. So if you look here, we have 4 cash flows. So this would be, we say year 0 to year 3. Okay, so these would be our cash flows. And these are the dates they fall on, and this is the actual cash flow. So if we look at the more of a detail of the cash flow, I'll just say time up here. Okay, so the time, in year 0, we invest $300. The purchase of 3 shares is $100 per share. Year 1, we purchase 2 additional shares plus dividend. Year 2, dividends on 5 shares plus the sale of 1 share. And year 3, dividends on 4 shares plus the sale of 4 shares. So these are the total cash flows that make up this investment. So if we want to calculate the dollar-weighted return, we're going to use the Excel function internal rate of return. So I'm going to click on the internal rate of return. Let me just make this a little smaller here so you can see it. And all I have to do is highlight all the cash flows and hit done. And let me format this, open up this percentage. And this would be the return would be a negative 16%, a 0.16%. So in example 2, what if you had a 12-year time horizon with an investment that you bought it for 5, so the first year is a negative cash outflow because you're buying the investment. And in any particular year, you could be getting an increase in the share price as well as dividends or even loss in share price. So if we have all of the cash flows associated with the stock, and this could be how the investment is moving forward, and it's always assuming that you're reinvesting your income. So we can do, again, just click on the internal rate of return, highlight all the cash flows, and then hit done. And then we have here a 13.67% return. So simple enough to calculate that. And this is basically what this is why we call dollar weighted, is because this is looking at the change in cash flows from dividends, buying and selling the stock, reinvesting the dividends over the lifetime, and then eventually selling the position down to 0 at the end. So that would be our dollar weighted return. Okay, let's move to arithmetic and geometric mean. So here, what we could do is we want to first get the sum. So we could use, there's an auto sum function in Excel here, and it's this little summation here. So I can just do a quick auto sum. N would be the number of periods here, which are 10. And then the mean would simply be the sum divided by the period. So this would be the arithmetic mean. Now you can also calculate this in Excel. So if we just type in mean or average, so in calc just type in average and highlight all of these. And we get the same result, but this is using the Excel. Let me just do that again. Done. And you see here that, let's move this over. Okay, so this is just using the total sum divided by the n. And in the second equation, I'm using the average. And you see how we get the same result. Okay. Now the geometric mean, which is using a compound rate. So first we take the total return, and then to get the relative return, we're going to take one minus the return. So you see here, 1 plus the return. So 1 plus -3 is 97. 1 plus 30% is 1.3. So you get it. So we're just taking 1 plus in this column here. Now, when we calculate, so n is just going to be the number of periods 10. And then we could use that when we calculate using the longhand formula, and then we divide it by 1 by n. So this would be the exponent of 1/10 minus 1. To calculate the geometric mean, I can just look up geomean, and then I'm going to highlight all the cash flows, all the relative return, and then hit done. At the end of it, though, I do have to still say -1, like in the formula here, to get that geomean. So the arithmetic mean is 18.76, but the geomean is 18%. Now, try to calculate on these two handouts below here by yourself. Pause the video. When you return, I'll go over the calculation. Okay, so here I suggest using the average formula and just highlighting the cells to calculate the average. Well, let's try that again. Okay, so it gives us the average. And then if you do it the long way, of course, you can use the sum function and just highlight, and then you have 5, and of course 100 divided by 5 is the 20. So both ways work. Here, using the geo mean, you use geomean as a function, highlight these return aspects here, hit done, but we have to -1 if we want to just have the geomean. Okay, let's look at the inflation rate, inflation adjusted returns. So here we have the formula from the textbook: 1 plus the total return divided by 1 plus the inflation rate -1. So this gives us the inflation adjusted rate. So you can see that it's not simply total return minus inflation rate. We get a rate that is different than that, so slightly smaller. And this is the formula up here. So pretty simple to calculate inflation adjusted rate of return. Okay, standard deviation. So here in the standard deviation, in the first example, I have it filled out for you. So we have the probabilities, and these have to equal 100%, which you can see at the bottom. We have a quick calculation here of average, count, and sum. So this is the summation, the n, and the sum, as 1 is 100%. Here are the holding period returns. And then if we just multiply column B by C, so that makes more sense now in the spreadsheet than in the slide. So we just multiply these across, and then we find the sum of this column to get the expected return. So the mean from the deviation from the mean is really the deviation from the expected return. So we're going to take C4 minus D8. Remember that D8 has these absolute positions, so you could easily just pull the formula down. And then here, what we're going to do is the way this is calculated is column B, the probability, multiplied by the square deviation. So problem B multiplied, and here we have that formula again, the C4 minus D8 to the square root. But we already have that calculated here, so we could take a shortcut and just say probability times the mean deviation to the exponent 2, and we get the same result. And so we could just pull this down, and you see that we get all the same results here. Okay, now here the variance is just going to be the sum of these is the variance, and to get the standard deviation we're going to use the square root function, the square root of 8. Okay, so now that I've gone over that, try the example 2, pause the video and try example 2. When you return, I'll go over example 2. Okay, so here we're just going to find the sum, and we could use the sum formula. So we're just going to take the sum of these, and this is basically probability times the holding period return. You see that these are all calculated that way. So we find, so this is the expected return is 10.87%, but we leave that as a whole number because it's easier to do the calculation. So the mean, the deviation from the mean, so this expected return is really the mean here. So we can kind of just say it's the mean. Now, so we want to take, just like we did up here, we want to take the C4 minus, but this time we're going to do D18. So we're going to go C4 minus D18, but here I'm going to put absolutes to lock down that cell, so I can just pull this down. And then to calculate, I'm going to take, okay, so I'm going to take the probability and multiply it by the deviation from the mean to the exponent 2. If I do that for all of them, I get my, find the sum of this, and I'll get my variation. Highlight the range. So this is my variation, and then calculate the square root. Use the square root function. Oops. Clicked on the wrong spreadsheet there. Try it again. Take the variance and find the square root of the variance. And this is my standard deviation for example 2. Okay, let's move on to, close this, move on to the effective annual rate. So the nominal annual rate of interest is also the APR, annual rate. So that's our nominal rate. So to calculate the effective annual rate, if the what we call n-pari in Excel, which is a frequency, an annual frequency will have the nominal rate in the year will be the same. Semi-annual, quarterly, and monthly will be slightly higher because we're compounding on interest. So in Excel, we can use the formula effect. So I'm going to go to formulas, insert function, search for effect. Okay, and then I'm going to put in the nominal rate, and then n-pari, which is 1. And done. So you see that's 8%. So for the next one, it's going to be the same nominal rate, but now n-pari is going to be 2. Oops, put that in the wrong set. Hold on. So doing this for each of them. you can see how the effective annual rate increases with the compounding. Now you try it on this second example. Pause the video and try it, and then restart the video. Okay, so here's another shortcut I can use. I can just say, and you probably were wondering why I didn't do this before. I can just set up the formula here, and then I can just pull it down by grabbing when the white plus turns to a black plus. I can just pull that down and get the, and you see below it's going to bring all the formatting. So let me just keep the formatting the same. Okay, so that would be how you calculate the effective annual rate from the nominal or APR. Okay, in this table here, we have the year, the market rate minus the risk-free rate, and then we have the returns for treasury bills, and so we should really call this T-bills, bonds, stocks. Now, if you look here, if we take G4, divide by 100 plus 1, we get this is sort of a total return relative. This going back here, this is when we calculated this to be total return TR, and this is like the relative return. Okay, stocks. And then this would be total return bills, treasury bills. Okay, so this is just data from a number of years in the past. And we're going to use this data to calculate the arithmetic mean. So you can see that that's just the average of the T-bill column E. The bonds is the average of the bond column. And stocks is the average of the stock column. Okay, so the risk premium here, we're seeing, I made this in yellow because the risk premium is going to be the the treasury bonds minus the treasury bills. And for the stocks, it will be the stock minus the treasury bills. That gives us a risk premium because this is risk-free. Standard deviation, we could use this standard deviation .S formula where we just highlight the column, and that'll give us the standard deviation for treasury bills, T-bonds, and stocks. And then the min-max, if I use a min and a max function, it will search the column to give me the lowest variable and the highest variable to give us the range. So moving down here, putting these ranges of time periods in here, we can calculate the market return as an average for these periods, the market return, standard deviation using that same formula, and then the Sharpe ratio. So for each of these periods, so this is 20. This is the biggest period, followed by breaking the period up into three pieces. We can see how these different periods of time reflect in standard deviation, market return, and Sharpe ratio. It's actually pronounced Sharpe ratio, but I always mispronounce it to say Sharpie. But the Sharpe ratio, so I just put this little note down here so you understand. The higher the Sharpe ratio, the better. So this would be I would say, based on the Sharpe ratio, this is the best period of time. And you can also see it has the highest market return, but also the highest standard deviation. So with the Sharpe ratio is going to be a measure of risk-adjusted return in the portfolio. So the higher this ratio is considered superior to the peers. So it's going to measure the excess portfolio return over the risk-free rate relative to its standard deviation. So that's why we calculate these. And so the higher the better. Usually we're saying a Sharpe ratio greater than 1 is considered acceptable and good by investors. 2 is very good. 3 is amazing. Anything under 1 is suboptimal. So these portfolios that we're looking at, this market return, which is the average of, this is the column here, which is the market return minus the risk-free rate is already calculated there. So the market itself is not optimal, but finding a subsection of stocks within the market, you might be able to produce a Sharpe ratio higher than the market. So this would be your baseline to look at how your portfolio would be risk-wise and Sharpe ratio-wise compared to the overall broad market. Okay, so that's the whole spreadsheet. So basically what I'm doing here is just, again, summarizing some of the main points of the chapter and then utilizing Excel to show you how to do the calculations for the material in the chapter. Okay, thanks. I hope you found this helpful, and I'll talk to you next time.